Hello and good evening to everyone. Welcome to week 8 problem solving session for theory of computation. Hi Ankit. Welcome to week 8 problem solving session. Okay, we are just getting started. So like always, what I'll do is I'll solve a few questions on the previous assignment and then a few questions on this week's content, so that it will help you both to understand the previous week's content as well as this week's content. Okay. So yeah, let's begin. So with this week's topic is decidability and reductions. But additionally, uh, okay, so last week's topic is this is last week's topic, and this is on undecidability. Okay, or simply this week's topic is on reduction. Okay, so let me start. So here's this question from the previous assignment. Okay. Oh, by the way, I'm audible, right?
Yes, sir. You are audible.
Okay, good. Thank you. Okay, yeah. So the first question is: consider the languages defined below. Okay. Here, s is a positive integer valued function that takes as input the description of a DFA shown by this m. Okay. M is the DFA, and this angular bracket shows that this is the description. So it's given as a string in some encoding. So we have two languages given to us. The first one is what is called inf DFA. Okay, what is inf DFA? It is all those descriptions of DFAs such that M is a DFA and the language of M is an infinite language. And next is the next language is ARB DFA. Okay, subscript S. ARB DFA S is all those strings which represent DFAs. Okay, such that M is a DFA. Additionally, LM, the language of the machine M, contains a string of length key which is greater than S of M, whatever this function is. Okay, so S is here. So how they have they defined S? S is a positive integer value function. Okay, so S takes some description of a DFA and then gives a natural number. That is what we are saying. Yeah. So, but just for ease, you can just take it k greater than some small s. Let's say. Let's not confuse ourselves by thinking about s to be a function. Okay, let's just say it is small s. Okay, s equals s of m. So k is greater than s. That's all we are saying. Now, first question we are asking is inf DFA decidable? Okay, this is the first question. What does it mean? Is checking whether M is a checking whether the language of DFA is infinite or not. Is that decidable? Okay, that is the first option. Second option is the complement inf DFA. What is the complement? They are saying the complement is eDFA and is therefore recognizable. Why? Because eDFA is co-recognizable. Okay, what is eDFA? Let me remind you. eDFA is checking whether DFA, the language of DFA, is empty or not. Checking whether the language of DFA is empty or not. They are saying, okay, the opposite of inf DFA, okay, or the complement of inf DFA, this language, is all those DFAs whose language is empty, and therefore it is recognizable. Okay, that's what they're saying, because this guy is co-recognizable. Okay. And finally, we have ARB DFAs. Okay. Yeah. So there we are saying ARB DFAs. Remember, ARB DFAs is all those machines, all those DFAs. Okay, whose language contain a string of length k greater than s of m. Right. So greater than s, let's say small s. Okay, and we are saying our DFAs is equal to inf DFAs if s is equal to number of states in the DFA. And finally, what are we saying? The complement of inf DFA is recognizable. Okay. Now let's see. Okay. Well, firstly, what we notice is, okay, uh, we'll say B. We'll look at B. Okay, first. B is saying inf DFA is the complement of EDFA. Now, can that be true? This is set of all DFAs. Okay, set of all DFAs such that the language of the DFA is empty. This is the set of all DFAs such that the language of the DFA is infinite, or in other words, is infinite or not finite. Now, what is the complement of this? The complement of eDFA is the set of all DFAs such that the language of DFA, okay, is not finite. Okay, so it means, so what does it mean? It is non-empty. So the language of DFA could be some could be 0, or it could be 1, or it could be 0 1, 0, yeah, 0 as well as 1, or 0 1 0 0, anything, but it cannot be empty. It cannot be empty. That's what it's saying. But here clearly infinite DFA says, oh, the language of DFA itself is infinite. So for example, something like uh, something like 0 0 0 0 0 0 0 0 0 0 and so on. A DFA accepting this language, okay, is contained in this set. Getting it? And examples here are this. But notice, okay, that a DFA accepting this, just 0, okay, DFA accepting just 0 is contained in this set. Is contained in this set, eDFA. Right? Because the language of that DFA is 0. Okay, it has one particular string out there. So it is non-empty, so it is an eDFA. But it is not an infinite DFA because the language is not infinite. It is a finite language. So firstly, we refute this claim. So infinite DFA is not equal to eDFA. Okay. So B is clearly wrong. They are saying infinite DFA is a complement of EDF. So, oh sorry, eDFA complement. Okay. So therefore, recognizable. That is wrong. Next, we'll look at this one. Okay, let's do a simpler one. The complement of inf DFA is recognizable. Okay. Now let's look at D. Right. So complement of inf DFA. What is the complement of inf DFA? Complement of inf DFA is all those DFAs, okay, such that the language of the DFA is finite. Now, what does it mean when the language of DFA is finite? Now we are asking, is this recognizable? The option is saying inf DFA is recognizable. Now the question is this recognizable? Is this recognizable? Can we determine if the language of a DFA is finite? That is the question, right? And okay, I'll come to this actually. Sorry, I started with D. Should have started with C. Okay, C says, okay, I'll come back to D. Okay, this is to be continued. C says, okay, arbitrary DFA equals inf DFA if S equals number of states in the DFA. Inf DFA if S equals number of states in DFA. Now this is really interesting. What we are saying is, in other words, okay, what is S? S is LM contains a string of length k greater than S. Okay, so it means, okay, and RBDFAs are all those DFAs which accept strings that contain strings of length greater than S. Okay, now we are saying RBDFA is equal to inf DFA, that is RBDFAs contains all strings that are of length greater than S. Okay, and inf DFA is all those DFAs which accept infinite language. Or in other words, a DFA, okay, in other words, a DFA accepts an infinite language. A DFA, arbitrary DFA, accepts an infinite language, okay, if it accepts a string more than the number of states in the DFA. Okay, this is the definition of RDFA, right? It is all those DFAs which contains a string of greater than S. But we are saying, what is S? S is the number of states. So RDFA is all those machines which contain a string of length greater than the number of states, right? So what is, for this particular S, RDFA, where S is number of states, it means it is the set of all DFAs which accept strings of length greater than the number of states. Then what happens? Then it is equal to inf DFA. And what is infinite DFA? It is all those DFAs whose language is infinite. So in other words, RDFA S. Okay. In other words, okay, I'll make it further more simple, that any DFA accepting a string whose length is greater than number of states is accepts an infinite language. Any DFA accepting a string whose length is greater than the number of states accepts an infinite language. You guys might have seen this before. Okay, this was used in a proof of a lemma. And what is the name of the lemma? It might be used indirectly. It was a pumping lemma. If you remember, the proof went like, okay, there is a DFA with several states and there should be a loop somewhere, and this is my pumping length P and so on. But what it simply means is, consider a DFA, okay? Consider a DFA, and this DFA does not have any self loops, okay? No self loops. Does not have any self loops and no cycles. What does cycle mean? A path that starts from one vertex and ends with on the same vertex. Okay, no cycles like this. No self loops, no cycles. Question is, and maybe something like this is allowed. Okay, this is still not a cycle, but if I make it this way, then it becomes a cycle. Okay, so no self loops, no cycles. Okay, question is, can it accept an infinite language? And the answer is clearly no. Because what is the maximum length of a language? What is the maximum length of a string that you can accept? Well, you go here, 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 and here. Okay, the length is 4, and here, here, and you stop. Length is 2, here, here, here. Length is 3, and so on. It's all finite. If the DFA computation ends in a finite number of steps, it's always there are, any string is of finite length that gets accepted by this DFA, and therefore this DFA cannot accept an infinite language.
So, sir, if
Yeah.
it has a self loop in case, then it can accept infinite language.
Exactly. I'll give you an example. Yeah, Ankit. So if I have a self loop here, okay. So for example, 0, 1, 0. Let's say if I have even one self loop, okay, then what kind of strings will it accept? 0, 0, 1, or 0, 1 first, okay, and 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, and so on. Or in short, 0, 0, star 1. Right? Okay, if this is the final state. Right? And what is this language? This language is infinite, right? Right, Ankit? Are you convinced?
Understood, sir.
Yeah. So,
Yes, sir. Yes, sir.
yeah, right. And or to add to it, not just self loops, even cycle is enough. Something like this is enough. Even if you have a cycle like this somewhere, it can keep accepting strings like this. Got it? So if this is, let's say, 0, 1, 0, and let's say this is the final state. Okay, and what kind of strings will it accept? It'll accept an epsilon. It'll accept a 0, 1, 0. It'll accept a 0, 1, 0, 0. Okay, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, and so on. Or 0, 1, 0 cube, in other words. Even if there is a cycle anywhere in the DFA, it will accept an infinite length. Okay. So, number of states. Okay. Now. Okay. Now, what does it mean? That okay. Now, why? What is it to do with the length of the string? Okay. Now, here's a nice trick. What is it to do with the length of the string? Okay. Take a DFA. Take any DFA. Okay. Let's say number of states equals n. Okay. And this is the DFA. And Q0, Q1, and so on till Qn. Okay. This is your DFA, and there are some final states. And say DFA accepts a string W of length n plus 1. What do you mean by n plus 1? It is more than the number of states. It accepts a string which is more than the number of states. What does it mean? On every symbol, I'm visiting exactly one state. Right? On one symbol, I'm visiting one state. Another symbol, I'm visiting another state. Another symbol, I'm visiting another state. And another symbol, I'm visiting another state. On every symbol, I'm visiting some state. Okay. And if I have, that means if I have n plus 1 symbols, I'm visiting how many states? N plus 1 states, right? If I visit n plus 1 symbols, then n plus 1 states are visited. But what is the problem with this? If I don't have cycles or loops, the problem is problem is the following. Problem is that I have only n states in DFA. Getting it? I have only n states in the DFA, but I'm visiting n plus 1 states. What can it only mean? It means some state is visited twice or more than once. Getting it? So,
Yes, sir. Getting.
yeah, okay, getting it?
Yes, sir. Yes, sir.
Yeah, right. So I keep visiting and I accept a string of n plus 1 and I'll say, oh, okay, there are only n many states. If I visited n plus 1 many state, I must have repeated some state. And how did I repeat a state? By a self loop or by a cycle. This means either self loop or a cycle present in the DFA. But what is the problem? If what does it mean if there is a self loop or a cycle? What can we tell about the language accepted by the DFA if there is a self loop or a cycle?
It can be infinite language.
Yes. In fact, it is always an infinite language, right?
Yes, sir.
Nice. Yeah. So language of the DFA is infinite. Getting it? So if you look at this option C, ARP DFA DS of S, okay, and what is S here? S is the, okay, this is S, okay, right. So ARP DFA S is equal to infinite DFA if S is the number of states of DFA. This is true. Why? Because S is the number of states of the DFA. So this is the number of states of the DFA, right? It means ARP DFA is all the DFAs who accept a string of length more than the number of states. Meaning what? It is nothing but it means that the language of RPF, language of these machines are infinite, infinite in size. Okay, and what is that? Nothing. It is nothing but this language. It is a set of all DFAs which accepts infinite language. So C is true. C is true. Okay. Now once that I've told you this, it becomes very simple. Okay. Now think about it for a while. How inf DFA is decidable? Why is it decidable? Can you think of an algorithm to, given a DFA, can you think of an algorithm to or a Turing machine to actually decide if the given DFA is accepts an infinite language or not? What does it mean for a language to be decidable? There is a Turing machine computing the language such that the language of the Turing machine is computes this given language, okay, given problem, and Turing machine always halts. I want an algorithm that always halts. So it is simple. As I've said before, if there are self loop, it means it is infinite. If there are no self loops, then the language can only accept finite strings, finite number of strings. So this is a litmus test for it. So algorithm, simply look at the DA phase description. Look at DA phase description. Okay. Description. Okay. If self loop slash or cycles found in the transitions, then output yes, otherwise output no. And this algorithm will always halt, because why will this always halt? This halts as DFA is always of finite size. So this is a finite process. I just go over each state. I look at each state and check if there are self loops. As soon as I see a self loop, oh, okay, it's accepting an infinite language. And if self loops are not found, my next I need to check if cycles are there. How do I check for cycles? I can do brute force. I can check for all possible subsets of states if there is a cycle present or not. Or I can use BFS, DFS, whatever. But anyway, the DFA is of finite size. It will take finite time to do this. And therefore, this will always halt and say yes, or it will say no. Okay. And so therefore, A is true. Infinite DFA is decidable. Complement of infinite DFA is recognizable. Now here, let me do a small recap. If this is decidable, it is contained in recognizable. Okay. If this is decidable, it is contained in recognizable and co-recognizable. Okay. So if L is here, then L bar will be here. Okay. And if L is in here, if L is here, okay, let me call it L prime is here, then L bar will also be the same language if it is decidable. So if it is decidable, it is closed under complementation. The argument is simple. If you were to say yes, you'll just say no. If you were to say no, then you just say yes. Okay. But anyway, this is a quick thing. So the question is saying complement of inf DFA is recognizable. So where did we put inf DFA? We said that okay, it is decidable. We said it is decidable. So inf DFA is here. So since inf DFA is decidable, the complement of inf DFA is also in decidable, and since decidable itself is inside recognizable, it is both inside co-recognizable and recognizable. So it means complement of inf DFA is in Turing recognizable. Okay, so this part is also true. Complement of inf DFA is recognizable. Okay. So I hope this question was clear before we move to the next one. Ankit and Akshay.
Yes, sir.
Okay. Okay, good. Akshay. Yeah. Okay. Yeah. Now next question. Okay, this is on bijections. Okay, so this is more of a discrete maths kind of exercise. So this is the question asked in the assignment. How many of the following sets are countably infinite? In the below options, the notation square brackets of 10 stands for the set square bracket 10 equals 1, 2, 3, 4 till 10, and this capital N stands for set of all natural numbers. So this is just standard notation. So the question is saying set of all rational numbers that have an even denominator. So I think you guys have already seen the idea for but I'll quickly talk about countable and uncountable. So countably there are several kind of infinities, okay, and there are larger infinities and smaller infinities, as you may have seen in the lectures. So countably infinite is the sort of smaller kind of infinity. Countably infinite meaning what? I can enumerate or sort of list them down, list all elements without skipping any. I can always list countably infinite set. For example, natural numbers. This because natural numbers I can list them as follows. I can write them as 1, then 2, then 3, 4, and so on. Then when I reach 10, uh, I'll just put 1, 1, 1, 2, and so on. And there's a certain scheme so that every n in capital N is reached, is listed. Nothing will get missed out if I follow this order. And if this is not possible, then set is uncountable. So this is much larger in a sense. I cannot even list them. I cannot even hope to list them out. A good example is real numbers. So why are real numbers? Well, there is a so I want to ask here that both of you have know the concept of diagonalization, Cantor's diagonalization. Cantor's proof that the size of natural numbers is not equal to the size of real numbers. If not, I shall repeat it.
No.
No, right? Okay. So here is the claim. Okay, this was proved by Cantor in some 1800s or something. This is the birth of set theory. This is how he proved set. He started set theory. The claim is that the size of natural numbers is not equal to the size of real numbers, even though both of them are infinite, and they are both of them are very large, right? It's both of them are infinities, but strangely, the natural numbers infinity is not the same as real numbers infinity. So why he said this is countable? I can list them out. This is not countable. This cannot be counted. I'll tell you how he did it. Okay. This is called Cantor's argument, Cantor's theorem. Cantor's argument, which is also called diagonalization. Okay. So he said that say R is countable. All the real numbers are countable. If it is countable, then I can list them. Then R can be listed. All the elements of R can be listed. So let me list them. Okay. So he said, let's list them. Let's say first number is 0.00000 and so on. Or okay, let's say they follow an arbitrary list 0, 1, 0, 2, 3, 1, 0, 4, 5, and so on. Real numbers can, the decimal point can go till infinity, right? And say the next number is 1.45327 and so on, and next is 1.3307012 and so on, and then he listed them. And our assumption is R is countable, And if R is countable, it can be listed so that no element is missed. Such that no element is missed, no number is missed. Okay. Cantor showed that I will show you a number that is not in the list. Okay. Cantor showed that he said that I will show you a number that is not in this list. But how can that happen? Because no element was supposed to be missed, no? So it gives us a contradiction that R is countable. This assumption was wrong. Okay, how he did it was as follows. He took the first number from the first, first digit from the first member of the list, second digit from the second member of the list, third digit from the third member of the list, fourth number from the fourth member of the list, and so on. I get an infinitely long real number. Then what he did, you know what he did? So he added 1 to it. Okay, 0 becomes 1, 4 becomes 5, 3 becomes 4, 4 becomes 5, and let's say here there was 8, then 8 became 9, and if there is a 9, then make it 0, and if there is a 9, say, okay, if there was a 9 here, then make it 0, and so on. 1.54590 and so on. This number will not appear in the list. Why? Because this number differs at first position from first number. It differs from second position at second position from second number, third position from third number, fourth position from fourth number. See, the first position is 1, and the first position of the first number, okay, I'll number it, 1, 2, 3, 4, and so on. Okay, and if the first position of the first number is 0, he made it 1. Second position of second number is 5. So he made a number that differs from every number in the list. Getting it? Because if that number appears at a position I, then it differs at the ith position in the list. So he made sure that it differs from all the positions in the list. It does not appear in the listing. So this property is violated about countable sets that, you know, all the members should be there in the list. So what does it mean? That it means that the real numbers are not countable. Okay, so this method is what is called diagonalization. Shows a contradiction. So you guys fine with it?
Yes, sir.
Okay. Akshay?
Yes, sir.
Okay, yeah. So the first one says set of rational numbers that have an even denominator. Okay. First of all, how many of the following sets are countably infinite? Okay. Out of these, how many? 3, 4, 5, whatever. Okay. So set of all rational numbers that have an even denominator. Okay, this I'll leave it as an exercise, this one, because this is a very standard thing. Because I'll just tell you right away. It's like this. You list them out like 1, 2, 3, 4, 5, 6, 7, 8, and so on. And 1, 2, 3, 4, 5, 6, 7, 8, and so on. And this is 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 2 by 1, 2 by 2, 2 by 3, and so on. 3 by 1, 3 by 2, 3 by 3, 4 by 3, and so on. Or 3 by 4, sorry. And 4, 5, 6, 4 by 1, 4 by 2, 4 by 3, and so on. So this, you see that this is rational numbers. No, rational numbers are all those numbers which are fractions, P by Q form. And to write it as a single list is not clear because it forms a matrix. It forms a two-dimensional structure. We want to make it a one-dimensional list. What we do is we traverse it this way, and so on. First member in my list is 1 by 1. Then next member is 2 by 1. Then next member is 1 by 2. Then next member is 3 by 1. Then 2 by 2. Then 1 by 3. Then next number is 4 by 1. Then 4 by 2. Then, okay, did I make a mistake here?
3 by 2, sir.
3
4
by
by 1 and then 3 by 2.
3 by 2. Oh yeah, sorry. 4 by 1. Then 3 by 2. Then 2 by 3. Then 1 by 4, and so on. Okay. And so if I maintain this zigzag order, then I will never miss out any member in the list. Yeah, good. Yeah. So this will never miss out any member in the list, and you can actually find a formula that will give you what is the position in the list also. So that I'll leave it as an exercise. Okay. So this argument is a famous argument, okay, which shows that rational numbers shown by this q is countably infinite. It's what is it asking? The question is asking rational numbers with even denominator. Let me call it q even. This is just q with even denominator. So obviously q even is a subset of q, right? And q, this is rational numbers. This is rational numbers with even denominator. I'll just pick out those elements which have even denominator. And clearly, if this is countable, then obviously this will also be countable. It cannot be that my subset or smaller set that I take is actually countably infinite. No, sorry, uncountably infinite. No. So suddenly, if I take a smaller set, it cannot be that it is much larger than the original set. So this is also countable. So clearly, this is good. This is countable. Next is set of all functions of the form f10. Okay, what does this mean? According to this, it means f takes a number from 1 to 10 and gives a natural number. Okay, f takes a number from 1 to 10 and gives a natural number. Right. Question is asking if it is countable or not. Set of all functions, set of all such functions that takes 1 to 10 and gives a natural number. Well, let's see. Okay, so there is another. If there are, okay, remember this, if there are two sets A and B and you want to find the number of functions from A to B is equal to size of B whole to the power size of A. Okay. Why? Because see, a function looks like this. A function looks like this. One particular function maps to an element here. Another can map to the same element here. It could map to another element also, unique element also. But something like this is not allowed. Okay. Something like that is not allowed. Something like if I take f, it cannot be that f of A is equal to B and C at the same time. It can only be a single element. F of A can only be B, and A and B can map to C, but a single B cannot be mapped to by two different elements. It cannot be like this. Sorry, what am I saying, man? Okay, it cannot be like.
You are saying oppositely.
Yeah.
Sir, you are saying opposite.
Yeah, the opposite. Sorry, yeah, that's what. This something like this is not allowed. A maps to both B and C. This is not allowed.
Yes, sir. Yes, sir.
Right. Okay. So quickly, I'll tell you how do you count such functions. Okay. This you may have seen in discrete maths. For every
Because it can happen for one value, say f of 1 and f of minus 1, they can have same output.
They can have the same output. Good. So
Because,
yeah.
yes,
So if I take an output here, how many choices do I have here? Size of a many choices, which map to B, right? Any element in B will have size of a many choices that it could get mapped to by. So, but you don't need to know this. I'm just for completeness sake. So every element in B, you have size of a many choices. Next element of B, I have size of a many choices, and so on. Sorry, the other way around. Size of B, and so on. And finally, it becomes size of B to the power A. Anyway, this is all you need. Okay, number of functions from A to B is size of B to the power size of A. Okay, now what is the size of this function? Yes, what is the number of such functions that take? What is the size of this set? 10. What is the size of this set? Size of n. Right. So what is the total size? So we are saying we want to count functions of the type which take this is of size 10, because this is 1, 2, 3, and so on till 10, and maps to all the natural numbers. So what is the size? Number of functions is equal to size of natural numbers to the power 10. Okay, and this is also countable because n is countable. Okay, this is multiplying by at most by again countable factor, so it won't matter. So it's some size of n times size of n times and so on. It'll still be countable. So this is not very large. Okay, and but this one is interesting. A set of all functions that map from a natural number to 10. One moment. Yeah, that's right. Okay, so let's look at C. Okay, size of what is the number of functions which map a natural number to 1 to 10. Now this is interesting because what does it look like? What is the what is the size of function? What is the number of such functions? Second set to the power first set, 10 to the power size of natural numbers. Now we are doing 10 to the power natural number. Now this is a huge number. Okay, n to the power huge number. 10 to the power huge number.
yes, sir.
Yeah,
It is infinite.
yeah.
It tends to infinite.
It tends to infinity, but there is certain confusion. But it is definitely tending to infinity. But is it countably infinite or uncountably infinite? No. Getting my question?
Yes, sir, getting.
So the answer is uncountably infinite. I'll show you why. Okay, because I can use diagonalization again. Okay, so we want to count the number of functions. No. So let's say say set of all functions, okay, of the form f natural number, which takes in a natural number and gives some value between 1 to 10, is countable. Then it means it is listable also. So let me list them. Let's say this is the first function, this is the second function, this is the third function, this is the fourth function, and so on. And this maps the behavior of the function. Okay. On seeing the natural number 1, f of n gives a 0. Okay, sorry, or a 1. And on seeing a 2, it gives a 10. On seeing a 3, it gives a 9. On seeing a 4, it gives a 7. And on seeing a 5, it gives again a 7, and so on. But all the entries are in 1 to 10. Each entry is contained in the set 1 to 10. And f2's behavior is like, okay, when input to f2 is 1, we get 9. When input to f2 is 2, then we get 3. But remember, the entries are again always within 10. Okay, and this goes on 7, 8, 9, 10, and so on. This key can keep going up till infinity, because this is actually the set of all natural numbers. Because remember, our domain is natural numbers. F can take any input. Each of these functions can take any natural number as input. What do we simply do? We apply Cantor's diagonalization. Once again, I take the diagonal and add 1 to it. Plus 1, plus 1, plus 1, plus 1. Then I get 2, 3, something, 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 something. And this is the behavior of a function, some f. Let me call it g. G is this function that does not appear on list. So this contradicted the fact that the set of all such functions is listable, right? So it means that set of all such functions is not countable. Set is uncountable. Getting it? Is this clear? It's the same diagonalization principle but applied to functions. Let me know if there are any queries. Akshay and Ankit.
No, sir.
Okay.
Okay. Okay, good. Okay, so okay, which one was uncountable? This one is uncountable. So immediately, see, even in 10, when the entries were from 1 to 10, it was uncountable. Same argument will show, okay, now the entries are any natural number. Same argument will show that this is also uncountable, right? This guy is from same argument. Okay, this the set of all finite length strings formed from the alphabet 10. This I'll leave it to you as an exercise. This is very simple. As if you can list it, try to list out all binary strings. Okay, try to get a formula for a list of all binary strings. Okay, by a certain order. Let's say 0 followed by a 1 followed by 0 1 1 0 1 1 and so on. Get a list of binary strings. Then naturally this also follows, because yeah, alphabet. So now this you are treating as an alphabet. No, this you are treating as an alphabet. So what is the decimal system? Decimal system is 0, 1, 2, 3 and so on till 9, then 10, then 1, 1 and so on. But you have a 0 here. You don't have a 0 here, but instead you have a 10 here. But even this is listable, right? So this is also listable. So, but the exact listing, try to find out. Okay, and I leave that as an exercise. But what do you have? You have that this is listable, that is countable. This is also countable, and finally this is also countable. So what is the answer? 3. 3 sets from all these 5 are actually countable. Okay. Okay, so those were some exercises. Okay, so these are now simple questions on decidability. Okay, so this can be quickly handled. The question says select all decidable languages. Okay, here I give you a certain piece of advice. You don't need to think in very low level about decidability. Okay, you don't need to necessarily think about Turing machines. You can always think about algorithms instead of Turing machines, because of the Church Turing thesis, which says that Turing machines and algorithms are equivalent. So anything an algorithm can do, and a Turing machine can do, and vice versa. Okay. So instead of thinking in a low level about tapes and so on, if it helps, always think about just general algorithm. For example, you want to check whether uh, this is decidable or not. Ask the question: is there an algorithm which can solve this problem? My input to this algorithm is a word, okay, a string, and is the string of this form. That is all. Okay. So quickly we notice that A is of the form W reverse, such that W is 0 1 star. Now W reverse is a context free language, actually a non-deterministic context free language, but that's fine. So it has a PDA, and PDA is a weaker machine than Turing machine. Okay, Turing machine has an infinitely long tape. PDA has a stack. So any PDA can be simulated by a Turing machine. Turing machines are more powerful. It can, in fact, you can use Turing machines. You can use Turing machines tape as a stack and work as a PDA only, push down automate. Okay, and therefore this is decidable. An alternate way to see it is, given you need to construct an algorithm that checks whether your word is of this form, your string is of this form. Now this you know easily how to do. Okay, you just try different splits, try all possible splits, okay, of UV. Okay, try all possible splits. For example, something like 101, 101. Try this split first, and check whether the reverse of this is equal to this. Next, check 101, 101. Next split would be this, and check. It will say no. Next split would be 101, 101. At this point, reverse is same, so you say yes. So this is an algorithm, right? This is not. I'm not describing it a Turing machine, but this is still fine. As long as I say the algorithm halts always, it means that a language is decidable. So A is decidable. Now let's look at B. A to the I, B to the J, C to the K. What it's saying is I plus J equals K. Now, same argument you can use here. It is a context-free language. I can use a stack. Okay, there is a way to do it. I'll keep increasing the stack and then decrease at the end and so on. But again, if you think about it in terms of algorithms, okay, given a string A, B, C, C, what I'll do is I'll maintain a counter. Okay, think of it like a C program. Okay, I'll maintain a counter. C equals 0. And when I see A, I'll increase the counter. If W at position I equals A, then C plus plus, and then WI equals B, then B plus plus. Okay, C is a bad name. D is my counter. Then E plus plus, and then finally I check whether the count of D plus E equals F, and WI equals C, right? Then F plus plus. Then check if A plus B equals, E plus, okay, D plus E equals F. If yes, then output yes. If no, then output no. So think of it in terms of algorithms. So this is also done. This is doable by an algorithm. This doable by an algorithm? Yes, it is again doable by algorithm. I'll just keep counting the number of zeros I see in the input, maintain a counter, count plus plus and so on. And then at the end, what do I do? What does 2 power n look like? Oh, then I just check whether it is a power of 2 by repeatedly dividing by 2. That is one way to do it. Otherwise, if I count it in binary, if you take it in terms of Turing machine, to the power n in binary will always look like this. It is 1 followed by several zeros. So this is also decidable. And finally, there are hash separated x1, x2, and so on, where each xi is a string, and xi is not equal to xj for all I not equal to xj. So none of xi and xj are identical with each other. I can simply, again, don't think of it in terms of Turing machines, think of it in terms of algorithms. I look at the first string, then I keep going right and compare it with every other string. I'm good. Then I go to the next string and compare with every other string. Then I go to the next string and compare with every other string. And this is also doable by an this process will always halt given any finite input. Okay, so all of these are decidable. So you might have answered this correct in the assignment. I just wanted to make sure that you are not bound by the rules of Turing machines. That is all I'm trying to convey. Okay, is this clear?
Yes, sir.
Okay.
Yes, sir.
Okay, good. So yeah, now we move to the topic of this week. Okay, that is reductions. Okay, so I'll add a page before. Okay. Now, what are reductions? Okay, a reduction is a way of transforming one problem to another. Okay, transforming one problem to another. Why is it helpful? It is helpful in proving undecidability. This is one of the most effective ways to do it, and it is still used in modern algorithms and complexity theory to solve one problem using another problem. So yeah, that is another way to state it. Reduction is a way to solve one problem using another problem. Okay, what does reduction look like? We say A many 1 reduces to B. Okay, this is many 1. Okay, if and A and B are languages. Okay, A and B are languages. Then if a string x belongs to A, okay, first of all, if there is a function sigma which takes in some string and gives us another string, okay, such that if some string belongs to A, if and only if, then it is necessary and sufficient that sigma of x belongs to B. Now, what does it mean? It means given a problem, okay, and I want to build a and sigma is computable by a total Turing machine. See, I want to build a Turing machine. I want to build an algorithm that solves problem A. Reductions help in saying that to solve A, it is enough that I have an algorithm for B. That is what I'm saying. How? Let's say this is the solver I want to make. I'll call it A solver. Okay. It accepts, this Turing machine accepts all the strings that are in the language A. Okay. But I don't know how to create it. But I'm saying I can create this A solver if there is a B solver. Okay. So this is a Turing machine called A solver or an algorithm called A solver. an input when it is given to us, okay, and I want to ask whether it belongs to A or not. That is, yes means X is in A and no means X is not in A. And I want to use B solver. Okay, I want to use B solver for it. What I'll do is I'll do some surgery on it, on the input, and I'll cleverly transform it as B's input. Okay, sigma is a function which will transform X into sigma of X and give it to the B solver. Now B solver is will be fooled by it. Okay, will be fooled by sigma of X. It will be completely fooled. It will say yes or no on sigma X. Yes if sigma of X belongs to B, and no if sigma of X does not belong to B. So hello, hello.
Yes, sir.
Okay, is it somehow my
Yes.
writing is not visible? Are you able to see my writing? I mean, okay, yeah, it's
Yes, sir. Your screen is visible to us.
okay, okay,
It's
okay,
visible.
okay, okay, good. Thank you. Okay, so B solver will say yes or no. Thing is, okay, if B solver says yes, then A solver will also say yes, and B solver says no, then my A solver will also say no. And hence, okay, and we'll prove that okay, it is correct. We'll say it will always be correct, and we'll therefore show that, you know, having the sigma, having this sigma that'll do the surgery, it is enough to show that solving B solver, okay, is enough to solve A solver. Sorry, so, having a B solver, having an algorithm that solves B is enough to show that there is an algorithm that solves A. That is what I'm saying. Okay. So yeah, I think you saw some examples in the lecture, right? So I'm not going to dabble on that. I'm going to straightforward move on to a harder problem. Okay. I think you've seen examples of reduction in the lecture. I think regarding this ATM and halting problem, you've seen that ATM reduces to halting problem. Okay. Now, yeah, next thing I want to talk about is, like, let's say A reduces to B. Okay, let's say two languages, A reduces to B. Then what do you have? A reduces to B, and if A is undecidable, then B is also undecidable. Why? Because I clearly said if there is an algorithm that solves B, then there will be an algorithm that solves A, right? So if there is an algorithm that solves B, because if B is decidable, if B is decidable, then A would be decidable. But we assume that A is undecidable. Right. So that cannot be true. So it should be the case that if A is undecidable, then B is also undecidable. Getting it? Next, if B is decidable, then this directly follows from the definition of reducibility, then A is decidable. Because clearly if B is decidable, then there is a B solver for it. And if there is a B solver for it, then we clearly said that this entire box is actually decidable. This entire box halts always, in other words. Okay. So yeah, the first one is the technique to prove undecidability. You show that an undecidable problem reduces to your problem, therefore your problem is undecidable. Okay. Okay. So this is slightly on the more difficult side, I would say. Okay. But please let me know if you don't get something. Okay. Here is the question. HP101010 is the set of, okay, I think there are too many 10s. So I'll just call it HP101. Okay, HP101. What is HP101? It is the set of all machines, okay, descriptions of all machines, Turing machines, that halt on the input 101. Okay. Question is this language decidable or undecidable? My answer is HP101 is undecidable. Why? Because I'll prove this. Halting problem reduces to HP101. And so if you guys don't remember, halting problem is um, the set of HP is the set of all machines such that M halts on all inputs. Okay. So all the machines that halts on all inputs is in the halting problem. Or in other words, in terms of a problem, given a machine, determine whether it halts on all inputs. Okay. And HP101 is given a machine, does it halt on input 101? Okay. So this is my claim. Okay. HP many one reduces to HP101. Now we know that this is undecidable. We know that the halting problem is undecidable. If the halting problem is undecidable, it must be that HP101 is undecidable because HP reduces to it. Because what does reduction mean? Reduction means that if this is decidable, this would be decidable. But this is already undecidable, so it cannot be that an undecidable language is now decidable. So HP101 must be undecidable. Okay. So here is the reduction. Okay. Let's look at the box diagram once again. What I want to do is I want to make an HP solver using an HP101 solver. Input to HP101 is a machine, and input to HP is also a machine. So input to HP101 is sigma of x, which I'll call because it is a machine, I'll call it M prime. Okay. And its HP solver should say yes. Okay. If M prime halts on 101 and no if M prime does not halt on 101. And this is what the reduction should be looking like. And then if it says yes, it should say yes. If it says no, it should say no. This outside yes or no is for the bigger box. The bigger box is the HP solver. It says yes if M halts. Okay, it's just bad. M halts on all inputs. No if means M halts on does not halt. M does not always halt. This is what I want to make. And question is, how do I find such an M prime? Getting it? How do I find such an M prime such that when I give M prime to HP101 solver, that is, when I check whether M prime halts on 101, okay, I can blindly say that this capital M, the original machine I have, will always halt on all inputs. Okay, that is the question. So here is my reduction. Okay. Description of Turing machine M prime. Okay, now please let me know if this is a bit heavy. Okay, but this is more on the difficult side. Okay, description of Turing machine M prime. Now M prime is a machine that has its own input. Okay, take note of the fact that I'm not actually running this machine M prime. I'm not actively running this machine M prime. I'm just writing the description as a string. Okay, so behavior of M prime. So what does M prime behave like? On input some y. Okay, what am I going to do now? What M prime does is it runs M on okay, where should it run M on? That is the question. Okay. Okay, if it halts, if M halts, then what should happen? Then M prime should accept 101 always. Okay. Then check if y equals 101, then accept, else reject. Okay. Um, okay, so what M prime does is it cannot run the person. Okay, yeah, even this will work. Okay, so what we do is we run. Okay, we don't actually run it. Okay, this is just a description of M prime. What M prime does is we run M on Y only if M halts. Okay. Oh, I made a mistake. That's where input to halting problem is an M and an X. M and X. M halts on X. Okay. What we do is we run M on X. If M halts, what happens? Only then will step 2 get executed. Right? And only then will step 2 get executed. If step 2 gets executed, then I check whether input is 101. If it is 101, then I accept. Again, if M halts on X, then what happens? Then step 2 executed. If step 2 is executed, Y is only when Y is 101 does my machine accept. So M prime accepts what language? 101. And so M prime accepts 101. Right. This means M prime is in HP 101. But what is this? M halts on X means M comma X is in HP. So if HP solver, okay, is saying yes, M prime halts on 101, then HP solver will say, oh, M comma X halts on X. M halts on X. But if M does not halt on X, it is not in halting problem. Then what happens? If M does not halt on X, step 2 is never encountered, step 2 never reached, and so the language of the machine, M prime, is empty. It will not be able to accept any string. It will never be able to accept any string. So it is empty. And if it is empty, it means M prime is not in HP 101. So if HP 101 solver says no, then HP also says no to M comma X. Okay. Ankit, I think left. So Akshay, is this clear?
Yes, sir.
Okay. Okay, please let me know, because this is a bit not very straightforward to understand. Okay. Anyway, this equals Turing machine. So this reduction, I'll leave it up to you. I want to quickly do Rice's theorem now. That is another topic. Okay. Now things will get a bit simpler here. Okay. Rice's theorem says the following. Okay. Testing non-trivial property of language of any Turing machine is undecidable. So what does that mean? That means if L is of this form, given a machine, checking a certain property P is true or not. Okay, P is a non-trivial property, then L is undecidable. So this is a short method of proving something is undecidable or not. I'll come to what a non-trivial property is. But see, this is a language, and if the language consists of Turing machines, descriptions of Turing machines, such that some property needs to be satisfied, automatically I'll be able to say that it is undecidable. Provided what? Provided that the property is non-trivial. So what does non-trivial property means? Means not always true or not always false. It cannot be true for all machines. The property should not be false for all machines. What is an example? Example, say P of M has is the property that M has 24 states. So is this property trivial? This is not trivial. Why? Because I can always give a machine, because there are Turing machines such that have more than 24 states or less than 24 states, right? So this is a non-trivial property. So checking whether M has 24 states or not, given M, sorry, this is a bad example. What I'm talking the language. Okay, sorry, not the property of M. Really sorry, the language of M. This is yeah, not M has 24 states or not. Look at the language of M. Property of the language of M. property of the language of M is, for example, context free or not. Or let me be more simple. Language of M is non-empty. Language of M is not empty. This is undecidable. Why? Because the property is non-trivial. Because property is non-trivial. Why is it non-trivial? It means there are machines whose languages for which property is true, and there are machines whose languages has property false. Because there are true instances. Okay, for example, um, for non-empty, no. For example, I can make a machine with language um, 101 or sigma star, whatever, and false is a machine with language as empty. The trivially rejecting Turing machine, a Turing machine which always rejects, is this particular Turing machine, right? So I can always give an example of such a Turing machine. So for which it is true also, I can give an example for which it is false also. So this is a non-trivial property. If it is non-trivial, then this is undecidable. So this is a sure shot method. So now, because of this, we can quickly apply it to several languages, right? So here is a question. Okay, A is all those machines such that language of M is finite. All those machines such that language of M is finite. So is this property trivial or non-trivial? Trivial
I
meaning,
think it is.
yeah,
I think it is trivial.
you think it is trivial, but actually trivial means that for all machines the property is true, or for all machines the property is false. So is it true that for all machines, for any machine given, the language is always finite? Or is it always true that for all machines, for any machine given, the language of that machine is always infinite? So so that is what I meant by trivial. But okay, so but the answer is that it is actually non-trivial. Why? Because see, I can give you a machine, I can give you examples as follows: when the property is true, when the property is false. Okay, an example when the property is true is a machine, okay, whose language is finite. That is, which accepts, say, accepts only 0 and 1. This is finite. And I can always define a Turing machine that looks at the input. If it says 0, accept. If I look at the input, I see a 1, then accept. Otherwise, always reject. Now, false instance is a machine whose language is not finite. Okay, maybe this is why you said this is trivial, because to come up with an infinite language. So what the example here is a machine which accepts sigma star. What does it mean? That is accepts all inputs. It will accept on all inputs because sigma star is the set of all inputs. No? So there is an example for the true property being true. There is an example for the property being false. So this is a non-trivial property. Which means it is undecidable by Rice's theorem. Okay. So yeah, this one I want to ask you again, Akshay. This look at this one. Machines, okay, all those machines such that the language of the machine is regular. Is this trivial or non-trivial? Trivial means for any machine given, the property is always true, and or property is always false. Non-trivial meaning I can always give you an example of a machine where the property is true, and I can give you an example of a machine where the property is false. So any idea?
I think it is decidable.
It is
Decidable.
decidable.
Yes, sir.
How come? But okay. Before that, what do you think about the property? Is it trivial or non-trivial? Okay, or I ask you this question. Can you give me an example of a language which is trivial? Sorry, what am I saying? Can you give me an example of a language which is regular? Can you give me an example of a language which is regular?
0 star 1.
Zero star?
No, wait. 0 0 1 0 0 1 0
Okay.
0.
0 0 1 0 0 1 0 0 0 1 and so on, right?
Yeah, so
Yeah. This is clearly regular. Right. Yeah, good. So now I ask you the question, can you give me an example of a language which is not regular? Not regular. Maybe we've seen it in during pumping lemma, such languages. Some language that will definitely require some memory, more memory, I mean. So do you remember this language? 0 to the n, 1 to the n.
yes, sir. Including empty string.
Yeah, yeah.
It should include even empty string also. That one might be not regular.
Yeah, okay. Including empty string also we can put. But so is this language regular?
0 n 1 n is not regular.
This is not regular, right?
Yes, sir.
But this is regular.
Yes, sir.
And DFA, meaning I mean Turing machine can always mimic a DFA. So I can have a Turing machine which accepts this as my language, and I can have a Turing machine that accepts this as my language. Because my Turing machine will simply simulate the DFA. It will do whatever the DFA is doing. Okay, or in this case, it will do whatever the PDA is doing. And Turing machine, as you know, are as strong as algorithms. So computing this is not very difficult for it. But you get it right now. I give you you give me an example of a machine where the property is true, and you gave me an example of a machine M2 Okay, I give you an example of a machine M2 where the property is false. That the property, what is the property? It is regular. The property is that the language is regular. So for M1 it is true, for M2 it is false. So what does it mean? Is the property trivial or non-trivial?
Trivial, I think so.
This is true, this is false. Yeah?
I think it might be trivial.
No, but clearly the definition of non-trivial is that there is an example of a true, there is an example of a false. It's not always true. Okay, but okay. So since there, okay, I'll actually, okay, I get it. Uh, I get where the confusion is. See, I'll give you an example of a trivial property. Okay, so look at E. M is a set of machines. Okay, so the language is a set of machines such that the language of the machine is a subset of sigma star. Okay.
Okay.
Now, is this? I ask you now the question: is this property trivial or non-trivial? Can you give me a machine whose language is not a subset of sigma star? Can you give me a machine whose whose language is not a subset of sigma star? Is it possible? Yeah. So, can you, okay, so what is sigma star? Sigma star is 0, 1 star, no? And my language is also in the alphabet 0, 1. Can it be that my machine is computing something which is not in 0, 1 star? And 0, 1 star contains epsilon, 0, 1, 1, 0, everything, right? 0, 1 contains, 0, 1 star, that is sigma star, contains all possible strings. No. Any language I create I'll be picking elements from this sigma star only, right? So it is not possible to actually come up with a language which is not contained in sigma star. Because any language I come up with, right, will always pick elements from this set sigma star. Right? So this property is always true for all languages, for all machines. Turing machines. Okay, Akshay?
Okay, sir.
Okay, this property is always true for all machines. A given any machine, its language will always be contained in sigma star.
Okay. Yes, sir.
Yeah, right. So this is always true. I can never give you a machine for which it is false. So therefore, this is a trivial property. So such kind of properties are what are called trivial properties. It is always true for all machines. But look here, look here. See, here it is not true for all machines, clearly, right? Because for one machine I'm getting true, for one machine I'm getting false. So this, for if such kind of properties I'm going to call non-trivial properties. True, for one case it's true, for one case it's false, so it means it is non-trivial. Again, trivial means for all it is true, or for all it is false. But if I give you a machine for which it is true, for which it is false, then it is not. Then it is non-trivial. Okay, and if it is non-trivial, then by Rice's theorem it is undecidable. Okay. M words on all inputs. Okay. So let's do a final one. Okay. Uh, all the machines. Okay. Such that the language of M accepts 42. All those machines such that the language of the machine contains 42. Okay. Or the machine accepts 42. 42 belongs to the language, in other words. So think about it for a while. Do all machines, do all Turing machines that someone designs, okay, will it always accept 42? Given given any machine, I'm always guaranteed to am I always guaranteed that it accepts 42? Or can you give me an example of a machine that does not accept 42? Okay, 40. Okay, sorry. This 42 is a bit confusing because we were working in binary until now. Um, can you give me an example of a machine that uh, okay, that accepts 101? Can you give me an example of a language that does not contain 101? Yeah. Can you give me an example of a language that does not contain 101? It could be any language, could be regular. Okay. So see, for example, if I take a language, see what the one you've given, 0 0 1 0 0 1 0 0 0 1 and so on. This language does not contain 101. 101 is not contained in this language, right? So if I have a machine that accepts this language exactly, then it will not accept 101. But consider a machine whose language is like 101 101 101 101 101 101 and so on. Consider this language, then this machine will accept 101. So I have an example where the property is true that it accepts 101, and I have an example where the property is false. Getting it?
Yes, sir.
So if the property is true also, if I have example where it is property is true and I have an example where the property is false, then my language is it trivial or non-trivial? The property.
Not trivial.
Yeah, exactly. Non-trivial, right? So I have machines where it is true also. I have a machine where it is false also. So this is a non-trivial property, and this is undecided. Okay. So okay, little time left now. I just want to say one final thing that, see, testing the property is for the language of the machine. Okay, it is not for the machine itself. So, for example, here G is M such that M halts on all inputs. Rice's theorem is not applicable here because it does not say L of M. It says only M. That is a property of the machine. It is not the property of the language. Rice's theorem is only applicable for the. In this case, Rice's theorem will not help us. In these cases, the Rice's theorem will not help us. And in this case, I would like you to try this is undecidable by a reduction. Reduction, okay. But try reducing from halting problem. Okay. Okay, so with that, we'll end the session. Is there anything? No, I think that is it. Yeah, Akshay, is there any questions left? Okay, I'll stop the recording.
No.